Here's a machine that does exactly one thing. You type a sentence and it makes a short video clip. That's the whole job. Turn words into moving pictures that look right. Nobody ever handed it a depth map, never told it where a camera was standing, never showed it the outline of a person and asked it to trace one. All it was built to do, make convincing video. Now take that machine and retrain it, a second round, this one supervised on labeled examples, to do something it was never built for. Read a scene instead of generate one. How far is each object from the camera? Which way is this surface facing? Where exactly is the edge of that person in the frame? Train it on those, and it answers. And on depth, judging how far away everything is, the model that started as a video generator beats the ones built from scratch for nothing but learning how to see. That's the result. A video generator retrained to perceive, beating the models built to perceive. On depth, the task they went head-to-head on. And the team behind the paper thinks they found something much bigger than a party trick. First, the honest frame. This is an early preprint. One team, no independent replication yet, and the code isn't even out. We're looking at a first result, not a settled fact. But it's worth walking through because the finding itself is striking. The numbers are specific, and the claim they stack on top of it is exactly the kind of claim that deserves a closer look. The most direct comparison in the paper is depth. They match the fine-tuning, same data, same task, then swap in different pre-trained models and watch which one carries the most useful knowledge into the job. Start from the video generator and the relative depth error lands around 9%. Start instead from the models whose whole purpose was to learn good video features, and the error sits at 15% and 28%. Lower is better here. So the starting point that learned by making video transfers far better than the ones built to learn how to see. Same fine-tuning data, different pre-trained starting point. That's the gap they're pointing at. And it's not just those learners. Give the repurposed generator more to train on, and it lands right in the pack of the best purpose-built depth systems, the specialized tools that do nothing but this. It beats some, comes in a whisker behind the very best, but a video generator landing in that conversation at all next to systems engineered from the ground up for depth, that's already the surprising part. The generator is a model called WEN 2.1, an open text-to-video system, the same breed as the clip generators you've watched flood your feed this past year. The researchers take its insides and with that same supervised retraining, push further. They fold many of these tasks into one model steered by a text prompt. Ask for depth, it renders depth. Ask for the outline, it traces the object. Ask where the camera is, it tells you. Ask for the joints of a human body, it maps them. Jobs that each used to need their own specialized system, coming out of one backbone, chosen by what you ask. And here's why the team is excited. For years, computer vision has been a workshop full of specialized tools. One model for depth, a different one for outlines, another for pose. Language went the opposite way. It found a single recipe, predict the next word, and that one objective quietly collapsed translation, summarizing, all of it into one general model. Vision never found its version of that. The paper's bet is that generating video is it. To make a whole clip look convincing, the argument goes, a model has no choice but to internalize geometry and objects and the way things sit in space. And that's the same machinery perception runs on. They call what's hiding inside the model a world model, and they say they've got strong evidence it's real. That's the leap. And it's bigger than what they showed. Because that comparison tells you which starting point wins, not why. And the starting points differ in nearly everything that could matter. Yes, the biggest generator is 14 billion parameters, dwarfing rivals under 2 billion. But size isn't the answer, because even the small generator, sitting right in their size class, still beats them. What's left uncontrolled runs deeper than size. These models were built differently, and above all, pre-trained differently. Different objectives, different data. WAN spent its entire pre-training learning to generate. The rivals didn't. So the win could come from the generative objective or from any of the rest. The authors say exactly that. Suggestive, they call it, not proof. The headline is louder than their own hedge. Then there's the number that really catches the eye. 7 to 500 times less training data. It's true, and it's about the last step, the fine-tuning at the end. What it leaves out is that one was already pre-trained on billions of images and videos before any of this began. It's efficient at the final mile. Call it efficient overall, and you've quietly dropped the most expensive part of the trip. And the one model does everything pitch, it's got a hole in it. Fold every task into that single generalist model and 3D body pose falls apart. The paper says training everything together severely degrades it, and the unified model doesn't even report a pose score. Credit to them for saying it out loud. The do-it-all model they're selling has a task-shaped gap where one task used to be. Now, here's the part underneath all of it. There's a deeper problem hiding in that phrase, world model. Reading depth, tracing an outline, finding the camera, that's perception. Pulling structure out of a frame that's sitting in front of you. It is not the same thing as understanding what the scene is about to do. That the ball caught midair is going to bounce. That the cup in the hand drops the instant the fingers open. A model can nail exactly where every object sits in space and still have no idea what happens next. Every piece of evidence in this paper is the first kind, reading what's there. The words world model reach for the second kind, knowing how it behaves. Those are two different claims, and only one of them got tested. So here's the honest state of it. The broad idea isn't new. Others have pulled perception skills out of other video generators, one even showing a whole spread of them in a single model. This exact result, though, is still one team's, unreplicated. One result like this is a finding. A pattern takes a few more. Subscribe and you'll see whether it grows into one. Because strip the grand claim away and what's left still stops you. A model built to do nothing but generate video. No perception labels anywhere in its training. Turns out to carry representations that, once you fine-tune them, outread the specialists. That much is real. The numbers earn it. What isn't earned is the why. And it matters which it is. If generating video is genuinely what teaches a machine to see, the payoff reaches far past this one model. There's a clean way to start pinning it down, and no one has run it at this scale. Hold the architecture, the size, and the data fixed, and vary only the objective. Do that here, and you'd finally know whether the generating is what did the work. Until someone does, generating video is a suspect with a good alibi and no fingerprint. And the most exciting explanation is still just the one we haven't ruled out.